All right, let's get started. While some more attendees are joining, welcome to our first Innovation Hub webinar for this new series, Fall 2023, where we will go through some, a number of masterclasses on piezoelectricity. And we've invited experts from within CTS and from academia for these events. So we hope to see you, and I hope to I hope you will get something interesting from these webinars. Today we'll start with an introduction of the webinar series and also about CTS, and we'll focus later on the Piezocomposites and how to optimize their designs using finite element modeling. I'll start with an introduction about composites, going through the types of composites, their features, advantages, and limitations, and then talk about manufacturing capabilities. And then my colleague Wei-Yi will talk about simulation, the FEM process, and give some some results and examples about how to run the process and what to expect. All right, at any time, please don't hesitate to write your questions in the interface. We have a Q&A function that is available. We will take the questions whenever we see them, or if it makes sense, then we'll just answer them at the end, depending on what's most relevant. But don't hesitate, there is actually also a chat in case that's of interest. But otherwise, the Q&A module is designed for that. All right. So starting with a few words about CTS, we are a designer and manufacturer of engineered solutions. And if you look at our product lines, we have two main product lines. The one we call AMS, Advanced Materials and Solutions, and Sensors and Mechatronics. Sensors and Mechatronics focuses mostly on automotive applications, with foot control sensors and actuators for automotive, whereas AMS is more component manufacturer. We also have controls, we have temperature sensing products, we have EMC, RF, and we have piezo. So today we are talking about piezo. And as you can see on the map, we are present across the globe as CTS, and actually also with the piezo capabilities, because we do have 6 locations for piezo across the globe. So we are here for you. Talking about piezo, some of our products, we do bulk ceramics, which is based on pressed powder. We do multi-layer through tape casting and interleaving with internal electrodes. And we do single crystal products for high performance applications. We also do thick film, so products that can be, or piezoelectric devices that can be printed, typically for higher frequency applications or for flexible applications. And then we have a range of devices and transducers that are designed using these products and adding some more features, assemblies, mechanical parts, wiring, and testing. The Innovation Hub that we're talking about today is the whole process for us, from the idea generation to entering the market. So here currently we are upstream with these webinars and online trainings in order to stimulate your ideas basically, and inform about what can be done and what are the advantages of the different designs. After that, we have we offer services where we go through an evaluation of ideas. We go through proof of concepts, pilot production, full-scale production. So we are present at all the stages, and we support our customers along the whole process. There's an email address there, dk.innovation@ctscorp.com. Don't hesitate to contact us if you have questions about the Innovation Hub process. And this is the series for the webinar series for this fall this year. So we start today with the webinar about composites and how to design them through FEM. And later on, in a couple of weeks, we have another webinar on lead-free piezos by my colleagues Erling and Baltra. And then another couple of weeks later, we have our first guest speaker talking about measurement of D33. And another couple of weeks later, yeah, I have to check the dates there, but we talk about textured ceramics with another guest speaker, Mark Fenton. And of course, today we are focusing on FEM of composites. All right, so let's start. I'd like to just to say a few words about composites to start with. What we call a composite is something or material that is made up of several parts or elements. Typically, when we talk about piezocomposites, we are talking about a piezo component, which is sometimes referred to as the filler material, and a matrix material, the resin. The reason why people are interested in composite can be, well, there are different reasons. One is to create anisotropy. This is something you can see, for example, in CFRP or carbon fiber reinforced plastics, where using the fibers, you can increase the strength in one or two directions and achieve some specific material properties. The material properties are typically intermediate, so they are related to both materials and they are somewhere in between. And that's actually the idea of making a composite you can tune, so you have more parameters to play with when you design a product and an application. Another purpose is to improve formability. So you wouldn't want to manufacture something out of glass, for example, but out of glass fiber reinforced composite, then it's much more flexible. And there are a few applications of composites, and everybody here has touched a composite before. But when we're talking about piezocomposites, the applications are primarily medical imaging, but also we see a lot of interest in sonar applications and also in therapeutic ultrasound for high intensity focus ultrasound, and finally for non-destructive testing. So these are the main applications for us, for CTS in terms of composites. Some definitions here. When you deal with composites, you might hear some, well, different types of composites, right? There is a naming convention for two-phase composites, so when you mix two materials together, and the convention is based on the number of, well, the connectivity, so the degrees of freedom for each of the phases. And each one is expressed as a digit, so it can be 1 or 0, 1, 2, and 3, whether it's connected in, well, no direction, 1 or 2 or 3 directions. Some of the popular ones are the 1-3. So in a 1-3 composite, if you look at the light phase here on the diagram, you see it's a pillar shaped, so it is connected in the Z direction, but separated in the X and Y direction. And if you look at the dark phase, it is actually connected in all 3 directions. So you can go in X, Y, and Z just following this one material. So this is why it's called a 1-3 composite. And we have the same 2-2 composites are connected in the plane X and Y for both phases. And then we have porous ceramics and piezo paint, which can be anything between 0-3 and 3-3. So depending on how much well, void or the secondary phase is present, there can be some connectivity in the 3 directions. Some other definitions that you will definitely hear when you talk about about composites is the pixel size. So pixel size is the material that is left. So the ceramic that is left, sorry, the width of ceramic. And the curve is the part that is removed between the ceramic pieces and typically filled with the resin. And the pitch is the sum of the two. Another parameter you will definitely use is the volume fraction. It's the ratio of the ceramic volume to the total volume. And you can see anything in terms of volume fraction, anything from even down to like 20% up to the 70% range. So there's a few parameters to deal with when designing a composite. Now, some of the features of composites and advantages, if you consider a solid ceramic plate, and look at the different modes, you will see that the first vibration mode that is coupled with the piezo effect will be along the largest dimension, so length, width, or planar, and that will be a relatively low frequency mode. If you want to use that plate in a thickness mode, then while you have to go past all these radial and length width modes, and you end up with a coupling coefficient which is called KT, as by definition. Whereas if you look at a 1-3 composite, each piece of ceramic is somewhat disconnected from the others. So the transmission of the wave in the X and Y direction is highly damped. If we push that to the extreme, the pillars are almost free. And in that case, if you have a linear structure like that is freely vibrating, then you have a coupling coefficient K33. And if you look at the data sheet here, you can see that for just a material that I picked here, there is a big difference in terms of coupling factor between KT and K33. So in the end, the composite plate will have a much higher coupling factor. And at the same time, we decouple the length, width, or planar modes. Another feature that is interesting for composites is the acoustic impedance. So as I mentioned that when you manufacture a composite, you end up with properties that are somewhere in between the two materials that you're using. In our case, we have a PZT ceramic that has a high acoustic impedance, and a resin that has a relatively low acoustic impedance. So acoustic impedance dictates the way a wave is transmitted between medium. And if you have a big difference in acoustic impedance, then most of the wave is going to be reflected at the interface. And if there is a small difference, then most of the wave is going to be transmitted. So we have this equation here that expresses the intensity of the reflected wave compared to the incident wave. So if there's a big difference, then the wave gets reflected. And you have to consider also that if you're doing medical imaging, you're interested in soft tissue that has a low acoustic impedance, around between 1 and 2 megaradians. And that is, I would say, a relatively poor matching to the PZT ceramic. So it will be difficult to send acoustic waves from the PZT to the tissue. And of course, there's different ways of doing that. You may have interface layers that help the transmission. But if you manufacture a composite, because you end up with an intermediate acoustic impedance, you will actually improve the transmission to, well, water or soft tissue in that case. Now, if we are talking about porous materials, porous ceramics, we have here some examples or some study on the different parameters or different properties of the materials. When I said you get a combination of or something that is intermediate between the two materials, it is intermediate, but it's not necessarily linear. And this is the case here with the porous material. It turns out that if you add porosity, so here we have graphs that go from 0 to 30% porosity, then you will affect the different parameters differently. So if we look at D33 here in green on the right-hand side, the top right graph, we can see that there is a small decrease in D33 as you increase the porosity, but it's only like 11%. And compared to that, the acoustic impedance here on the left side has a drop of 40%. So by playing with these parameters, so playing with the porosity, for example, you can change quite significantly the different parameters or the properties of the material. And this is very interesting. So to summarize the advantages and limitations, we have here with the composites a higher coupling coefficient. We can suppress lateral modes. We have a lower acoustic impedance, which means we can transfer energy better. So impedance matching between the piezo and low acoustic impedance material. We also reduce the quality factor because we mix the piezo material with the low quality factor material. So we reduce the overall QM, which increases the bandwidth of the material. At the same time, we also decrease the surface area, so we have a lower capacitance, and we improve the flexibility of the material. So this is how you make, for example, these curved transducers. This is by using a composite and just forming it to the right shape. On the other hand, not everybody wants to use composites. I would say the main limitation is the higher cost. There is more work involved in making a composite. We have also, yield issues. There's more processing, basically. So it does drive the cost up. And there are some other concerns that may change the choice or affect the choice of a composite. One of them is the temperature stability. The piezo ceramic is relatively stable with temperature, but the resin can have some more significant variation across temperature. And there are, of course, also manufacturing limitations. And I'm actually going to talk about that in the next slide when we talk about manufacturing. In any case, it does require careful design. There's a lot of parameters to define, and it's not straightforward. You cannot just switch from a solid plate to a composite and just expect it to work right away. All right, so in terms of manufacturing, we use a lot the Dyson fill method. So in the Dyson fill method, we start from a bulk ceramic material, and then we dice in two directions. So this is obviously for a 1-3 composite, which is again I would say the most popular one. But we can do a 2-2 composite just by dicing only once. We dice only in one direction, and then we fill with the resin in between, and then release by lapping the backbone to release the composite. I would say this is the most popular method. You will also find methods such as arrange and fill. It depends on the dimensions and also the fill factor. So in the arrange and fill, you start from smaller pieces that you put together so you can control the distance. It's usually for I would say lower frequency composites, because for a high frequency composite you will need some very, very small pieces, and that's not really practical. All right, capabilities. We do have some limitations. We have challenges with collapse of the pillars because we free the material, the ceramic material, and we have, of course, the cutting, dicing stress that is applied, and that may result in some pillars just falling off or being unstable. So there are different things that we need to consider. One thing is the stability. So we need the pillars to be a certain size, depending on how tall they are. And also we have some limitations in terms of blade thicknesses, availability of blade thicknesses. So this is just a table to give you some idea of what is feasible, especially for the very thin composites. One other manufacturing capability that I wanted to mention is the reactive ion etching. that we apply on our single crystal material. It is a dry etching process. It uses a chemical plasma to remove material. And we use that for high frequency composites. So when we have a very, very small and fine structure, and this is used for high frequency for intravascular ultrasound typically. All right, so if I were to sum up a little bit what I talked about, we have different types of composites, the 132203. We introduce a filler material, so new properties or new parameters that we can adjust and define. And also in terms of shape, dimensions, frequency, we introduce a lot of new parameters that need to be defined for a good composite design. And this is why FEM simulation is, well, required. At least it's a very good tool to optimize a design in a shorter period of time with a lower cost. And this is a good introduction for my colleague Wei-Yi, who's going to talk about FEM at the moment on piezocomposites. All right. Wei-Yi?
Yep. Thanks for Charles' introduction about composite side. So I will try to share my screen to the FEM. Let me see. Okay.
Yep.
Yep. Can you see the screen?
Yes, you're on.
Yep. So today I'm going to present the composite material simulation, and the software is based on Unscale. And Unscale, they do have some free kind of 10 core hours to use. So if everybody kind of interested on that software, everybody can download and try to use it. So today I'm going to give a simple tutorial for that software as well. So here is today's outline. First of all, I think Charles already gave a really detailed introduction about the composite. So here I will just briefly speak it. And second topic will be the tutorial software on Unscale. And the third topic will be the PZT composite. The number 4 will be the single crystal composite simulation, and I will give a brief summary of today's composite simulation. And here is the reason why we want to use composite, because we want to use simulation before we run in the fabrication process, because it can save some time, some money, and some material as well. And the bottom one is 2-2 composite, it looked like, and the right bottom is 1-3 composite, and I will try to use 1-3 composite to get a brief introduction about the simulation. And for the composite simulation, what we need is some material property. First of all is the piezoelectric material property. Here we use PZT, for example, and the other material is epoxy. So there are some key elements we need to know from the material. First of all, it's electric stiffness and piezoelectric constants and clamp dielectric constants and density of the of material. And last one will be the electrical mechanical coupling constants in here. So the epoxy, we will need the elastic stiffness and density. So based on this one, we can do some calculation. And where can we get this property? In CTS website, we do have a material property, and then we can get the PZT material and also single crystal material property in here as well. And based on this kind of property, we can do a theoretical calculation. based on different kind of density, clamp constants, and elastic stiffness and piezoelectric constants. This kind of fundamental property, based on different volume fraction, we can get different performance of our composite. And the most important three key element is electrical, mechanical coupling constants, and longitudinal velocity, and acoustic impedance. And in Charles' introduction, he also mentioned acoustic impedance is also important. That's right, because we need to as close to if we make a transducer for body tissue, we need to as lower as possible to close to body tissue kind of impedance. Then we can get a better image quality. And at the same time, we want the longitudinal velocity and KT or K33 need to be higher to get better bandwidth. So this is kind of trade-off. One is going low, one is going high. So so for the volume fraction, in our composite, it should be around like 30 to 70%, around this range, can get the best result. So based on that, I will talk about the software tutorial, and there's like 12 steps, and I will go through it, but I won't go really detailed, but it will be really simple if you just take a look. First of all, we will try to create a new project, and the most important things is you need to mention what kind of analysis you are going to do. So here we are trying to do the one-to composite, that kind of vibration simulation. So we want to select the mechanical dynamic in here, and also that kind of unit, we select a millimeter. And then step 2, we are going to choose different kind of material what we are going to use. First of all is piezoelectric material. In here, in this example, we select CTS PZT material, and it's called PMT3. And the other one is epoxy resin, and it's a kind of hard epoxy. So we just select in here, there's an epoxy, tons of material you can select, so you can play around with different kind of material and get the best performance you want. And step 3, we will try to create geometry. Here is kind of a unit cell. So first of all, we create a epoxy pillar, and then we fill the PZT inside. So there's this is kind of unit cell for PZT and epoxy. And after that, we go to step 4. We will try to make it as an array. So we go in X direction and Z direction. We just try to get like 5 by 5 in here. And later on, we will do the symmetric to X direction and Z direction to make it bigger. And step 5. So we need to define a time function. This is the function we later on we will apply on our piezo material. So here we are interested in about like 1 megahertz in this example. So we put driving frequency about 1 megahertz in here, and we insert this kind of time function. And then we need to do the mesh. Mesh is really important in simulation. So in here, you can based on the wavelengths, and then we can select how many elements in one wavelength. So the higher number will give you the more accurate result, but it will take longer time to do the calculation. So you need to try and error. Sometimes it doesn't mean it's higher the best. You need to find the proper number for your simulation. Okay. And step 7, we want to know where we apply our voltage on our material. So we need to create one electrode on the top, one electrode on the bottom, and then we apply the function we just built on step 5 and put the load on one side, and the other side we just ground it. And then we insert these two loaded to our simulation. And step 8, just like what I said, if we select the right boundary condition by using symmetry, it can lower the calculation time and also give a really accurate simulation result. So in here, in X and Z direction, we use symmetric boundary condition. Okay, and step 9, we need to give the simulation software how long does it need to be run. So in this case, because our interest is about like 1 megahertz to 2 megahertz. So in simulation running time, we don't want to let it run it for too long. If it's running for too long, then it also will take a lot of time for calculation, and it's not used. It's not suitable for this case. So we use 0.1 millisecond in here. And it's almost to the end, so we want to let the software know what kind of output we want to get. So in here, for example, I just put the shape data. So shape data means we want to see what kind of vibration, what kind of the plate will distort. So we will see the shape, what's look like, and it's also in Y direction. And here we also put the frequency we are interested in, 1 megahertz. So after we set up everything, so we just need to put our file on the cloud. So in Unscale software, we need to upload the raw material, and then they will do a calculation on cloud, and it will take like 3 minutes for this calculation. And then after 3 minutes, we will download the result, and we can do some calculation in backside. Here is for another impedance result. So we just download the result and then do the calculation. It just takes like few seconds to get the impedance result. So here we can see the resonant frequency is about around like 1.5 megahertz, and then the anti-resonant frequency is about like 2 megahertz. And based on this one, I do the shape data in here as well. So left-hand side, I try different kind of curve and aspect ratio, and also variance fraction is a little bit different. In black line is based on the tutorial design. So the aspect ratio means the height of the pillar is about like 3 times of the curve. So this one the black one give us really clean and sharp resonant frequency and anti-resonant frequency, same as the blue one. Blue one also good, but the red line is kind of not clear because the aspect ratio is not as good as design. This one is way low than what we expect. And here is the shape data, shape modeling. Let's see. So you can see it's kind of vibrating, and then from here it's more from the cross-section side, maybe you can see more clear. You can see the shape is kind of changing. Yep. So based on this kind of vibration, the material can generate kind of acoustic wave. And here is our PZT22 composite experiment and our simulation result. So in this experiment, we take the 22 composite, and then we measure it, and then get the result is about like 5.7 or 5.8 megahertz, and the anti-resonance frequency is about 7. And then we base on this kind of design and then run the simulation on scale, and also change the thickness and the curve size a little bit, and try to see what kind of strength we can get. So in here, we know if the thickness, 2-2 composite thickness is smaller, 260 micron, then we can get higher frequency in here compared to green and red curve. And also, if we change the curve to larger curve size, then it will go to lower frequency, but it just changed a little bit. It's not a lot. So this is for this 2-2 composite simulation. And here is another example for 1-3 composite. This one, the bottom side here is the measurement result. The measurement result is about 2.7 megahertz in resonant frequency, and anti-resonant frequency is about 3.6 megahertz. And we take this one as into unscale and run the simulation and change the curve size to see what's going on with the simulation, and figure out the simulation is quite similar to what we get in experiment. And we change the curve size from small 30 micron to 60 micron, and we can see the resonant frequency is a little bit shift to lower frequency. And this is what we get in last page. That's PowerPoint, yeah. So if we increase the curve size, we will lower the resonant frequency a little bit. And here is our example for our customer. So the customer want to know what kind of material they are going to use. So they give us the requirement. Is what they need is the capacitance between 71 nanofarad to 84 nanofarad, and the KT coupling factor need to be around like 0.66 to 0.72. So in our simulation, we select different kind of material. So we choose CTS 3203 and 3221, these two different material, and choose different curve size. Here is 35 micron, 40 micron, and 45 micron. And the volume fraction is about like 70 to 75. So it's similar, but the result is just only, I think only this one is getting better. So CTS 3221, hold on, this one, 3221, this one can get the best result in our simulation. So we can just give our customer, say, this material is best for your property. And here is another 2-2 composite by using different material. Here is we use 3257 in our material, and the target is 9 megahertz for anti-resonant frequency, and also they need the capacitance between 123 nanofarad and to 145 nanofarad, and KT need to be above 0.61. So here is our simulation. We try to get different thickness to reach the requirement, and the thickness is about like 195 micron to 200 micron. And once we get this thickness, we can give our manufacturing side, they can grind the material to this thickness and then get the performance like what they design. And here is another example for single crystal. So I took 3 different material. One is 20 PMMPT 28 PT. The other one is 32 PT, and the third one will be the pin material. Based on these 3 material, we do some 1-3 composite simulation, and we can see in 32 PT, based on the same aspect ratio and volume fraction, 32 PT can get the best KT in here. That means resonant frequency and anti-resonant frequency is much far away from each other compared to 28 PT and pin material. So 32 PT can give us a better performance in transducer design. And here is another 1-3 composite simulation. So in here, we just choose different material, but with the same curve size. And we can see the volume fraction is a little bit different because we changed the thickness to match the requirement they need. In here, they need the resonant frequency around 12 megahertz. So we just need to change the thickness a little bit in here in this simulation. And the bottom simulation will be we change the volume fraction. We keep the same volume fraction and change the thickness to reach the requirement for FC. FC means central frequency they are looking for. So in both simulation, we can see 32 PT material always give us higher KT. Here, we can get almost close to the theoretical high KT in here and here as well. And the last one will be the high-frequency composite simulation. In here, I took the some parameters like curve size about 4 micron and the pitch size is about 16 micron. And the piezo size will be 12 micron into simulation to see if we put this parameter inside the simulation, can we get the similar performance like what we make in manufacturing side. And then in the end, we see the impedance curve is really sharp and clear, and the resonant frequency is around like 46 megahertz and anti-resonant frequency is about like 81 megahertz. And this is really similar to what we get in our high-frequency composite manufacturing side. So in summary part, we know our simulation can play around with some parameters like aspect ratio or curve size and some thickness before we run in the mass production. So based on this one, we can save a lot of time and money because we know how to run the simulation. So modeling also can show some complexity, and also we can know more about our composite property as well. And in simulation modeling, we can expand the application for our piezo material. So this is what I have today. If you have any questions, just let me know. Thank you.
All right. Thank you, Wei-Yi. That was really interesting. So as Wei-Yi just mentioned, if you have any questions, don't hesitate to use the Q&A module or the chat, and we are still here for a few minutes to answer those questions. I'd really like the presentation. I think at one point you mentioned, I'll just ask you a question while everybody else is typing their question in. You mentioned that you were trying to find the ideal aspect ratio for a given material. How easy is it to find the ideal aspect ratio, and what are maybe the parameters that affect the design?
Well, that's a really good question. So in our simulation and our manufacturing side, I will say around 2 to 3 will be aspect ratio. 2 to 3 is the most typical design. But other than 2 to 3, you still can get really good result. But for the manufacturing, probably it will have some difficulty if the aspect ratio too high. More than 4, it's not easy to dice, or more than 5, it's not easy to dice. Yeah. Or if that aspect ratio lower than 1, then the performance won't be good as well. Okay. So I would say around like 2 to 3 will be the best design at the beginning.
Yeah, I suppose it depends also on the filler material as well, right?
Yes, that's right.
All right, thank you. There's a question from Martin. How do the simulations correspond to experimental results?
Okay, that's also another really good question. So in simulation, most of parameters are well designed. So there's no kind of crack inside, because in our real product, we probably, based on our Dyson field method, it probably will have some small defect, and that kind of defect in simulation, we won't see it. So in simulation, the result always, I would say always, better than real product. But I would say it's really close, but not exactly the same. Yeah.
I suppose the input data, so the quality of the material data that you have is really important.
Yes, that's correct.
There is a question from Nilesh. What happens when the cross section of the pillars change? So if it's a circle compared to a square or hexagon?
Well, that's another simulation topic, because in this free software simulation, for the square one, it's easy to simulate. But if we change to different kind of like circle or some different geometry, it also will change the performance. But I think the most important part is the filling ratio, the volume fraction.
Yep.
The volume fraction is dominate this kind of composite property. Yeah, so even its pillar is kind of circle pillar or square pillar or hexagonal pillar, I think it should be close, but it's not the same. Yeah, the result would be close, but not the same.
Okay, thank you.
Yep.
There's a question in the chat from Shoko. There are so many FEM tools. Any comments on how to choose, or you have specific reasons why you chose the one we use?
Okay, so this on-scale software, first of all, I think it was piezo in before. And piezo, this software is quite useful in piezo simulation. And I think a lot of academia, they use this software to do some simulation as well. So, and on scale, they purchase piezo, and then that's the reason why I start using on scale. Yeah, and also it has some free core hour for every month, 10 core hours you can use. So it's I would say it's a really good start to using on scale to practice some simulation.
Okay. Another question, what is the type of PZT that you use for this composite? I think you talked about several PZT types.
Yes. So for the tutorial, I use I think that's CTS. I can't remember what kind of type, but I think it's a hard PZT.
Well, I think we use both, right? So yeah. Because we manufacture composites using both the hard and soft PZT. Yeah. So for medical applications, it tends to be, well, imaging applications, it tends to be more the high dielectric types, the soft materials, like 3203 or 3257, which are quite popular for these applications. But if you are in a therapeutic application where it's important to generate higher power, then that would be a harder material like K1300 or NCE41. But I would say the choice of material is the same as if it was a solid ceramic, right? So you're going to choose in terms of whether you want more power or more sensitivity. And the fact that you're making a composite out of it just makes it even better, but it doesn't changes the reason why you choose a given ceramic to start with. And also the products will be very different. When we talk about hard PZT versus soft PZT, because for a medical application, we normally target very high frequencies, like 3 to 10 megahertz, or even higher. Whereas for a therapeutic application, it would be more in the 400 kilohertz, maybe up to 1 megahertz, but not the high frequencies. Yeah, very different designs. You're welcome. All right. If there are any more questions, now is the time. I'll just give you like 1 minute. I'll just share the screen for a second. That screen, yes. While we are looking for, waiting for questions. If not, I'll just make a short announcement. I corrected the date, so here you have the schedule for our next webinars. The next one in a couple of weeks, lead-free piezo ceramics, and then later on D33 measurement, and finally textured piezo with an analysis on the processing methods and the properties. All right, I think we are all set. I don't see any more questions. Again, if you have any, if you're any interest or further question or interest in our technology or the Innovation Hub, don't hesitate to contact us. There was the address, gk.innovation@ctscorp.com, or just visit the website CTS Corp and use the contact form. Right. I hope this was a good webinar for everybody in the attendance, and I wish you a good rest of your day and hope to see you in another future event. Thank you.
All right, thank you.